Hello dear students, I'm back again with another video, Physics for grade 12 students. On today's lesson, we are going to explain the angular momentum. But before we get started the new lesson, I'd like to remind you previous lessons when we talked about the Newton's second law for rotational motion. Torque is equal to moment of inertia, time is angular acceleration. Okay, and we solved all questions that related with the Newton's second law for rotational motion. Okay, on today's lesson, we are going to focus on the angular momentum. What is angular momentum? If you remember in grade 11, you studied about the translational or linear momentum. What is linear momentum? Linear momentum is the product of mass of an object to its velocity. Okay, linear momentum is equal to mass times velocity or the speed of the object. Okay, for example, so the symbol of momentum is P is equal to mass times velocity. Okay, what does linear momentum depend on? Depend on mass and velocity. Okay, this is linear momentum. Okay, we studied in grade 11. Okay, but in grade 12, instead of P, we have angular momentum. Instead of linear momentum, what we have? We have angular momentum. We can say instead of P, L, capital L is represented for the angular momentum. Mass, what is the rotational analog of mass? Moment of inertia. What is the rotational analog of mass in linear object? Is moment of inertia. Time is, what is the rotational analog of velocity or speed? Is angular speed. Okay, so what is this? This is the unit of angular momentum. What do you mean by capital L? This is, we can say this is angular momentum. Angular momentum. Okay, what about I? Moment of inertia. Its unit is kilogram meter square. What about this is angular speed? This is angular speed measured in radian per second. Okay, so what is the unit of angular momentum? Let's prove the unit of angular momentum. Its unit is what? I measured in what? Kilogram meter square times angular speed measured in what? Radian per second. If you remember in chapter 1, radian is the unit for the angular displacement, but actually the angular displacement, because it's equal to arc length over r, is the ratio between two lengths. Angular displacement is dimensionless. It has no unit in the SI unit, so that is why we assume that theta measured in rad, but in that case we have to remove. Why? Because rad is not the SI unit and it is dimensionless. Okay, if you remove this rad, what does remain? Kilogram meter square per second. Okay, what is this? This is the unit of angular momentum. What is angular momentum? Is the product of what? Rotating object is moment of inertia. The product of moment of inertia and angular speed about the same axis. Measured in what? Kilogram meter square per second square. But be careful, linear momentum measured in what? Kilogram meter per second. This is the unit of linear momentum. But kilogram meter square per second is the unit for angular momentum. Okay? Now we have some tips and some notes about the angular momentum. Okay? Angular momentum is directly proportional to the angular speed when moment of inertia is constant. According to this equation, L is equal to I omega. What is the relation between angular momentum and angular speed? Is directly proportional. But you have to say at constant moment of inertia. For example, let's say when angular speed increases, what happened to the angular momentum also increases, but at constant moment of inertia. Okay? So, what about angular momentum with the moment of inertia? Angular momentum with the moment of inertia is also directly proportional, but at constant angular speed. Okay, for example, when L is equal to I times omega. Okay, when moment of inertia increases, what happened to the angular momentum? Angular momentum also increases, but at constant angular speed. Okay, so in that case, we can find the relation between the angular momentum with the moment of inertia and the angular momentum with the angular speed. Okay, but what about the relation between this relation between moment of inertia? This is the main equation, I omega. Okay, so what about I? I is equal to what? L over omega. Okay, so in that case, what is the relation between moment of inertia and angular speed? Is inversely proportional. Inversely proportional. Okay, so what do I mean by that? It means that when moment of inertia increases, what happened to the angular speed? Decreases, but at constant what? At constant angular momentum. What is relation between moment of inertia and the angular speed? Is inversely proportional at constant angular momentum. Okay, for example, such as the ice skater, when the ice skaters extend his hands and feet away from his body, from his axis of rotation, in that case, what happened to the radius? Increases. When the radius increases, what happened to the moment of inertia? Moment of inertia also increases. When moment of inertia increases, angular speed decreases, but at constant angular momentum. Okay. What does the angular momentum depend on? As I mentioned before, moment of inertia and angular speed. Is it possible for two objects? How many objects? Two objects. Okay. Is it possible for two objects with the same mass? M1 is equal to M2. How many objects do we have? We have two objects. Okay. And the same rotational speed. We can say omega 1 is equal to omega 2. Same mass, same angular speed. Okay. To have different values of angular momentum, L1 is not equal to L2? Yes, of course. The answer is yes. How? Okay, let me explain. Why, if two objects with the same mass and same angular speed has different angular momentum? Because angular momentum does not depending only on mass and angular speed. Angular momentum is equal to I omega. Okay. For example, if the shape is ring, for the ring is equal to what? I is equal to what? mr squared times omega. Okay. So in this question, these two objects, they have the same mass, they have the same angular speed, but maybe different in shape, or maybe different in radius. Okay, so that is why it is possible to their angular momentum is different. Okay, yes, because angular momentum depends on moment of inertia, not only the mass, or yes, because they may differ in their radius or their shapes. So because of rotating object has inertia, it also possesses the momentum associated with it. It is rotational. This momentum is called angular momentum. Angular momentum is a vector quantity. What do you mean by vector quantity? It means that angular momentum has both magnitude and direction. Okay? Angular momentum has both magnitude and direction. So its direction has the same direction of angular speed. Okay? Its direction is the same direction of angular speed, because moment of inertia is scalar quantity. Be careful. It's always positive. Okay, but the angular speed and moment and the angular momentum can be positive and negative. For rigid body, the moment of inertia remain constant. Moment of inertia remain constant. If it is angular velocity doesn't change, thus the angular momentum remain constant. For rigid body, listen carefully please. For rigid body, what do you mean by rigid body? Is a body that during rotating, its shape, its radius, its mass doesn't change, such as a ceiling fan. Okay, the ceiling fan, it is a rigid body. Okay, during rotating, the ceiling fan, its radius doesn't change, its mass doesn't change, but we can control the angular speed of the ceiling fan. Okay, if we increase the angular speed of the ceiling fan, its moment of inertia doesn't change. Okay, in the case of slowing down the ceiling fan, the angular speed decreases, but moment of inertia doesn't change. Okay, if the moment of inertia is constant, what is relation between angular momentum and angular speed is directly proportional. It's very important, be careful. Okay, when the moment of inertia is constant, such as in a rigid body, such as a ceiling fan or bowling ball or any other object, that during rotating its shape doesn't change, its mass doesn't change, its distribution of mass doesn't change. In that case, angular momentum is directly proportional to the angular speed. Okay, according to this relation, L is equal to what? I omega. If I is constant, if I is what? Constant. What is relation between angular speed and angular momentum? In the case of speeding up, what happened to the angular speed? Increase. What about the angular momentum? Also increase. Can we say angular momentum is conserved in that case? No. For the rigid body, when angular speed changes, we cannot say the angular momentum is conserved or constant. It changes by changing angular speed. Okay? So, the moment of inertia is constant always. Moment of inertia is constant for what? For rigid body. For what? Rigid object or rigid body, such as a ceiling fan. Okay? In the ceiling fan, during rotating, the moment of inertia doesn't change. I is constant. I is constant. If angular speed increases, what happens? Angular momentum also increases. If angular speed decreases of a ceiling fan, what happens to the angular momentum? Also decreases. But in the case, if angular speed is constant, the moment of inertia is already constant. What happened to the angular momentum? Also constant. Constant times constant, also constant. So, when does the angular momentum, L, angular momentum, is conserved or constant for rigid body? You have to say at constant angular speed. Don't say at constant moment of inertia, because for rigid body, when we talk about the rigid body, it is moment of inertia is already constant, doesn't change. Okay, this is all about what? The moment of inertia and angular momentum for rigid body. Okay. So, as you can see in the note number 3, for rigid body, the moment of inertia remain constant. If it is angular velocity, doesn't change, thus the angular momentum remain constant. But if angular speed changes, angular momentum also changes. So, when does L is constant for rigid body? If omega final is equal to omega initial. Okay? Look at note number 4. If the angular velocity of rotated object increases or decreases, look, this note also related with the note number 3. If the angular velocity omega increase or decrease, the angular momentum also increase and decrease, but at constant moment of inertia. Okay, decreases. Okay. Note number 5. Listen carefully, please. Pay attention. It is very important. Objects whose moment of inertia changes. What do you mean by object whose moment of inertia changes? It means that this object is not rigid. Okay, non-rigid object, flexible object. What do you mean by flexible object? Like some object that during rotating its shape changes, decrease, its radius decrease or increase. As you can see in this object, over 1, okay? This object, if you look, the mass is constant, okay? The mass of this object is constant. But in the case of expanding, what happened to the radius? Expand. In the case of expand, what happened to the radius? Increase. When the radius increase, the distribution of mass away from the axis of rotation, what happened to the moment of inertia? Also increase. Why? Because moment of inertia is equal to mr squared. So when I increases, what happened to the angular speed? Angular speed decrease. Okay? What about L? L is constant. As I told you, I is equal to what? Is equal to L over omega. When does moment of inertia and angular speed inversely proportional to each other? At constant angular momentum. At constant what? Angular momentum. So if you rotate, if you give some angular acceleration and angular speed for this object, so in which case it is angular speed increases? When the object is compressed. In the case of compressed, what happened to the radius? Decrease. What happened to the moment of inertia? Decrease. So what about the angular speed? Because the moment of inertia decreased, it is angular speed must be increased to compensate the moment of inertia. So in that case, the angular momentum will be conserved. As you can see in this figure, in this video, look at this video. Axis. Look at this video. This is the same shape.
Through the sphere. We will note first that the moment of inertia in this expanded configuration is much larger.
In the expand configuration, in that case, this is axis of rotation. What is this? This is axis of rotation. More radius. Okay? So more radius provides more moment of inertia. More moment of inertia. But less angular speed and L, it becomes constant. Okay? Okay.
Larger than moment of inertia.
So in the case of compressed,
contracted configuration.
or decreased.
So what we can expect is that if we give it some angular momentum in the expanded high moment of inertia configuration.
This is high moment of inertia, less angular speed, okay? But same angular momentum. Okay?
And
look.
If we contract it, its angular speed should increase.
Look. In the case of when the object is compressed or the distribution of the mass is closest to the axis of rotation, in that case the radius, what happened to the radius of the shape decreased? Okay, in that case decreases, and also it is moment of inertia decreases, but it is angular speed increase, but angular momentum in the first case and in the second case is the same. Okay, look, more angular speed, less angular speed.
Sure enough. It's one of the most spectacular demonstrations, I think, of conservation of angular momentum.
Okay, I hope you understood well. Okay, let's go back to our slides. Objects whose moment of inertia changes, such as skaters or swimmers or any other object, have an opposite change with the angular speed. Whose angular momentum will be conserved. L is equal to what? I omega. When this is for flexible object. What do you mean by flexible object? The object that we can say the object during rotating, it is moment of inertia changes, decrease or increase. When moment of inertia decrease or increase, the angular speed also decrease or increase. But it is angular momentum conserved or constant or doesn't change. As you can see in this ice skater, okay, look at this Here, this student, okay, in the case when extend her arms are feet away from the axis of rotation, what happened to the radius? The radius increases. Okay. In the case of extend her hands and her feet away. Okay. So what happened to the radius? This is axis of rotation. R increase in the case of extend. In the case of extend, R increase. When R increase, what happened to the moment of inertia? Also increase, because R is directly proportional to the moment of inertia. So what about the angular speed? Decreases. But angular momentum is constant. In the second case, when the skater brings her hands close to his or to her body, in that case, what happened to the radius? R decreased in this case. Okay. So moment of inertia also decreased. What about the angular speed? Must be increased. But L still conserved or constant. Or you can say conserved. Okay. L is conserved. So let me ask you a question. We have two cases, figure number 1, figure number 2. In figure number 1, the ice skaters extended his or her hands and feet away. But in the second configuration, the second figure, the ice skaters closed her hands and feet toward its axis of rotation. So which one is bigger, L1 or L2? You have to say is equal. They have the same angular momentum. Why they have the same angular momentum? You have to say because angular momentum is equal to I omega. For flexible object, for non-rigid object, when angular speed increased, what happened to the moment of inertia? Decreased. So in that case, the angular momentum must be conserved. Okay, this is the conservation of angular momentum. So let me ask you a question. When does angular momentum be conserved? For ice skater, flexible object, and for rigid object. For the rigid object, such as a ceiling fan or any other rigid object. What do you mean by rigid objects? The rigid object, it means that the object that during rotating, it is shape, it is mass, it is radius doesn't change. Okay? So we can say the moment of inertia for the rigid body is constant. When does angular momentum is constant for rigid body? You have to say when the angular speed is constant. When omega is constant, the moment of inertia is already constant for rigid body, so that is why the angular momentum is constant. But for flexible object, when the moment of inertia changes during rotating, such as an ice skater or such as this hoverboard, this object, okay? So can we change the shape of this object? Yes, of course. Okay? So during the rotating also we can change the shape of this object. In that case, in which configuration the object has more angular momentum when it is rotating? In the case of compressed or expanding, in both cases the angular momentum doesn't change. Why? Because only the angular speed and the moment of inertia changes in that case. So finally we can say that for flexible object, for the objects whose moment of inertia changes during rotating, the angular speed and the moment of inertia changes inversely together. Okay? So in that case, the angular momentum is conserved. So for flexible object, when the angular speed changes, is it possible for the angular momentum to be conserved? Yes, of course. But for rigid body, such as a ceiling fan, when the angular speed changes, its angular momentum can never be conserved. Okay? Stationary object has zero angular speed and also has zero angular momentum and zero angular acceleration. Assuming the friction between the skaters and the ice is negligible, there is no friction, there is no resistance, and no torque acting on the skater. So his angular momentum is conserved. So when does Angular momentum is conserved when the net torque acting on the object is 0. Okay? When brings his hands and feet close to his body. Close. What do I mean by close to his body? It means that R decrease. I decrease, but angular speed increase. L is constant. In the case when he close hands and feet to his body, more of his mass near the axis of rotation, as the result, moment of inertia of his body decreases. Because his angular momentum is constant, that is why angular speed must be increased to compensate or pay back for the smaller moment of inertia. What is the rotation analog of linear momentum? Is angular momentum. Linear momentum represented by P, but angular momentum is L. Now, the law of conservation of angular momentum. What is the law of conservation of angular momentum? What do you mean by the conservation of angular momentum, such as the ice skater? It means that L initial is equal to L final. L initial, for example, assume that when the ice skater closes her hands and feet toward his body, okay, L final, the same ice skater when extended his or her hands and feet away from the axis of rotation from his body. So which one has more L, which one has more moment of inertia? They have the same. In these two configurations, these two figures, they have the same angular momentum. In the first case, Li is equal to what? Is equal to I initial, omega initial. The second case, I final, omega final. So which one has more angular speed? Which one has more angular speed? Initial or final? Initial or final? Absolutely the initial. Omega initial is bigger than omega final. Why? Because in the omega, for the first case, when he brings his hands and feet close to his body, in that case, we have less moment of inertia and more angular speed. But in that case, we have more moment of inertia and less angular speed. Okay, for the look. But I initial is less than I final. But the angular momentum in both cases is equal. This is the conservation of angular momentum. This is for one object, one system, such as the ice skaters. When the net, but in that, when does L initial is equal to L final? When net torque is equal to 0. When the net external torque acting on an object or object is 0, the angular momentum of the object or object doesn't change. This is the law of conservation of angular momentum. Okay, for flexible object. Initial angular momentum is equal to final angular momentum. Under which conditions is the angular momentum of object conserved? If the net torque is 0. When? If the net torque acting on object is equal to 0. For example, if there is no torque acting on the ice skater, so his angular momentum is always conserved. Another question, under which conditions is the net torque on an object becomes 0? If the object rotates with a constant angular speed, or its angular momentum is conserved. In these two cases, the net torque acting on the object becomes 0. Does stationary object have angular momentum? Stationary object have angular momentum? No. What do you mean by stationary? Stationary, it means that omega is 0. When omega is 0, L is equal to what? I omega. L is equal to 0 for stationary object. Do stationary object have moment of inertia? Yes, of course. Because moment of inertia does not depending on angular speed. It depends on mass, radius, and the distribution of mass around the axis of rotation, which means that it's a shape. Okay? So, do the stationary objects have angular momentum? No. Do the stationary object have moment of inertia? Yes. Because stationary or rotated object have both mass and radius. Okay? Question 24 from chapter review. Look at this question. Is angular momentum always conserved? This is very good question, guys. Listen carefully. Is the angular momentum is always conserved? Absolutely no. The angular momentum is not conserved even for the ice skater if there is a net torque acting on the ice skater. Okay? For example, for the ice skater, Li is not equal to Lf if the net torque acting on the object is not equal to 0. In the presence of the torque, the angular momentum can never be conserved. This is the first case. The second case, even in the absence of the torque, L is equal to I omega. This is for rigid body, sorry. This is for what? For rigid body. For rigid body, the angular momentum is always conserved? No. When does it become conserved? When angular speed is conserved. Okay? So the answer is absolutely no. Only when there is no external torque on the system, the angular momentum L is conserved. Okay? So here we have some rotational analogs. So it is very important, and it has been brought many times in the Wizari exam. So the rotational analog for torque, we can say the rotational analog for force is torque. The rotational analog for mass, as I mentioned before, the moment of inertia. This is F, this is torque. This is mass, this is moment of inertia. For linear momentum, we have angular momentum. For linear speed, which is V, we have angular speed. For linear acceleration, we have angular acceleration. What is this? These are the rotational analog for linear quantities or translational quantities. Okay? Look at question 26. Very good question, guys. Listen carefully about the angular momentum for the object consisting of, for the system consisting of two objects, a merry-go and a student on the merry-go. A child on a merry-go-round moves from the near the axis to the outer edge of the merry-go, as you can see in this picture. What is this? This is the merry-go, and this is the axis of rotation of the merry-go. The merry-go is rotating at first. When the child moves from near the axis to the outer edge of the merry-go, what happens to the rotational speed of the merry-go-round? And explain. Look. So we have two distance of the student from the axis of rotation. What is this? This is merry-go. Okay. Assume that this is the radius of the merry-go. At first, the student is here. Okay. This is R initial. What is this? This is R initial. After a while, the student moves away from the near axis to the outer axis. This is R final. What happened to the final radius? Radius increased or decreased? In that case, radius decreased. Why? Because R final is bigger than R initial. The child moves away to the outer edge of the merry-go. What happened to the radius of this student? Increased. If the radius increased, what happened to the moment of inertia? Also increased, because this student has a point mass on the rotating object. Its moment of inertia is equal to mr squared. When R increases, I also increases. So what about the angular speed? Angular speed must be decreased to compensate the decreasing of the of the moment of inertia. But in both cases, L initial is equal to L final. But R final is bigger than R initial. I final also bigger than I initial. But final angular speed less than initial angular speed for the moment of inertia, for the angular momentum to be conserved. What happened to the rotational speed? The rotational speed must be decreased. Angular speed must be decreased. Angular speed decreases because moment of inertia has increased, requiring slower rotational speed for angular momentum to be conserved. I increase, omega decrease, rotational kinetic energy we will study in the next lessons, inshallah. But in that case, R also increases, but L doesn't change. Okay? As you can see here, rotational kinetic energy is equal to 1 over 2L omega. This is for conservation of angular momentum. Is it possible, question 27, is it possible for an ice skater to change his rotational speed omega without any external torque? Yes, of course. Without any external torque, the ice skaters can control their speeds or his speeds. The ice skater can increase its angular speed and it is decrease its angular speed. By changing what? By changing the moment of inertia. When the ice skater increases its moment of inertia, angular speed decreases by extending his hands and feet away. But by closing hands and feet close to the axis of rotation, what happened to the moment of inertia? The moment of inertia decreases, then the angular speed must be increased, so the angular momentum is conserved. Yes, of course, we can change the angular speed without an external torque. How? By making his arms close to his body, so the moment of inertia decreases, angular speed increases according to the law of the conservation of angular momentum. L is constant. Okay, so we have two tips here, two notes. When he brings his hands and feet away, in that case, what happened to the radius? Increase. Moment of inertia? Increase. But angular speed? Decrease. Angular momentum? Constant. When he brings his hands and feet close to his body, in that case, R decrease, moment of inertia decrease, angular speed increase to compensate or to pay back the decreasing of moment inertia. Therefore, the angular momentum will be conserved. Okay? The law of conservation of angular momentum for skaters, one object is equal to I initial times omega initial is equal to I final times omega, which was, this equation is based from this. Okay? But for system consisting of two objects, in that case, such as when the students on a merry-go, look, for example, if we have a merry-go or cylinder rotating around a specific axis, okay, if a child is on a merry-go, at first is here and the second time is moving, this is R initial and this is R final, so this is the radius of the shape. Okay, in that case, how many objects do we have? Two, the student and the rigid geometric shape, which is the merry-go. So in that case, L initial is equal to L final. L initial is equal to I initial for the student plus, I initial for student plus I initial for what? For the geometric shape, merry-go. Time is, this angular speed is the same at first because according to the rotational object, every point on the rotating object at the same point, they have the same angular speed. When the child is here at this point, point A, and the merry-go is rotating, which one has more angular speed? The child or the merry-go? Both of them, they have the same. Is equal to this side. I final, when the child is moved from near the axis of rotation to the outer edge of the merry-go, in that case, its moment of inertia changes. So this is final moment of inertia for student. This is final moment of inertia for what? For merry-go. Time is omega final. But listen carefully, please. The moment of inertia for the rigid object doesn't change. They have the same. I initial is equal to I final for what? For rigid object. Rigid body such as merry-go, merry-go-round, cylinder or ring, bicycle tire. For every rigid object, the moment of inertia, initial moment of inertia and final moment of inertia doesn't change. But the moment of inertia of this child is not the same. Okay? The moment of inertia changes. I initial for the student can never be equal to the I final for the student when the student changes its position. Okay? Inshallah, in the next lesson, we are going to solve all questions that related with the law of conservation of angular momentum. After that, we will study the rotational kinetic energy. Thank you for listening. Keep up your best doing. See you again, inshallah.